All right, good. So let's get started. So PSET 3 was out yesterday. As you may have seen, it is due Friday of next week. Okay, and that'll be the last PSET before the midterm, I guess. Okay, well, we'll talk about the midterm later. But so last week we sort of finished on sort of pure computability theory. We talked about how do you prove that some language is equivalent to the halting problem, right? And you can do it via reduction, okay, using the central concept of an oracle, right? You show that if you had an oracle to solve your problem, then you could also solve the halting problem. That's then a proof that your problem must also be uncomputable, and not only uncomputable, but in the same Turing degree as the halting problem. Okay, and and sometimes these proofs can be interesting. We did a couple examples. And the other thing is that it may be of interest to know that your problem is at least no harder than the halting problem, right? And so or that your problem is recursively enumerable, as they say. That is, that there exists a program that when you run it for infinite time will list all of the yes inputs, of your language. Will list all of the strings that are in your language. That's what it means for a language to be recursively enumerable, okay? And the halting problem is an excellent example, or the halt language is an excellent example of a language that is recursively enumerable but is not computable, okay? Thereby showing that those two concepts are different from each other. Okay, and so we saw last week sort of some techniques for showing that a language is recursively enumerable. And by the way, if you know that your language is recursively enumerable, then that sort of immediately implies that it's reducible to the halting problem, right? That's it's a stronger property. Okay, so we saw how you can dovetail, over all Turing machines, sort of running, you keep incrementing t and then running the first t machines for t time steps. Okay, very useful technique. And we saw Koenig's lemma that says that sort of if you can construct sort of arbitrarily long finite strings, that sort of satisfy some condition. In particular, if you can construct sort of if you have some tree with like a finite branching factor and you can construct arbitrarily long paths, finite paths through the tree, then in fact the tree must have an infinite path. Okay, also useful. Okay, and then we started talking about self-reference, which is where things really get fun, I think. Okay, and the issues of self-reference go back to the ancient Greeks, to the paradox of the liar, where you say this sentence is false. Okay, but it would be nice to be able to ignore these sort of puzzles by just saying, well, we don't care about sentences that talk about themselves, right? And that's it. But the problem with that, which was started to be realized in the early 20th century with people like Tarski and Gödel, is that sometimes you can once you have a powerful enough language, then sort of it will be able to express sentences that talk about themselves, whether you wanted that or not. Right, and so you're going to have to deal with it somehow, right? If you want, to be able to say that your whole, system of reasoning is, is sound, is consistent, is whatever. Okay, so in some sense, there's no avoiding self-reference. Okay, and one example is because you can always say something like the following sentence repeated twice the second time in quotes is false. and in quotes. The following sentence repeated twice, the second time in quotes is false, right? So then you have a sentence that's only talking about some other sentence that's in quotes, and yet indirectly it is talking about itself. Okay, and and a very a concrete analog of that is how it's possible to write a program that prints itself as output. So we saw how to do that. You can say print the following twice the second time in quotes, and then in quotes print the following twice the second time in quotes. Okay, it's a very good exercise. We're not going to put it on a PSAP, but if you've never done it, just take your favorite programming language and just write a program that does that. Write a non-empty program that that when you run it, its output is itself. Okay. You basically just have to, implement that, that pseudocode of, print the following twice the second time in quotes. Okay, and in recitation, you heard about sort of the recursion theorem, which basically says that given any program whatsoever, you can always assume without loss of generality that program takes its own code as an additional input. Okay, so that's sort of that's a form of self-reference that you can always satisfy. Okay, you can when you're writing a program, you're allowed to just say look at the source code of the program, even though by the very fact of writing the program, you're modifying the source code. Okay, there's always a consistent way to sort of solve that. To sort of unravel that circularity. And the essential idea of it is really just contained in the, in that print the following twice the second time in quotes example, right? Or you could say, take a program that just say print its own source code, and then you could compile it into, into that print the following twice the second time in quotes thing. Okay, so. All right, and then last week we started talking about Gödel's incompleteness theorem, which is sort of the most, sort of spectacular, a demonstration of all these ideas. Okay, so to say what Gödel's theorem is, you have to, say something, at least at an informal level, you have to say something about formal systems, okay, or proof systems. So a proof system is just, as we said, it's a collection so it's a formal language for expressing mathematical statements, and then a collection of axioms and rules of inference, and the rules of inference you can use to derive new statements, typically infinitely many statements, by just starting from the axioms. Okay, and the so the various properties that you might want a formal system to have. So you may want it to be sound, meaning everything that it says as a theorem is true. Okay, that sounds pretty obvious, right? A weaker condition than soundness, but which maybe we would settle for, is consistency. Okay, that at least it never says, it never proves both, a theorem and the negation of that theorem, right? The system should never both, say that both A and not A are true. Okay. Then computability, means that there should be some Turing machine that we could write down that lists all of the theorems of the system, okay, that lists everything that the system says is true. Or to put it another way, the set of theorems of our proof system should be recursively enumerable, okay? And then we really ambitiously, we might want our system to be complete. Okay, which would mean that given any sentence whatsoever that you can write in the language of the system can either prove it or it can prove its negation, right? So it sort of it determines the answer to everything. Okay, and then subject to all of these conditions, you may want your proof system to be as powerful as possible, meaning, that it should capture sort of as much of mathematical reasoning as you can get it to. Okay, so So then, that's sort of the context for, stating Gödel's first incompleteness theorem, okay? And what it basically says is that if you have, or sort of a weak form that, I can sort of talk about the proof of here, is that if you have a proof system F, and it's sound, and it's computable, and it's sort of, this is a little bit vague, but I'll be clear about it. It's powerful enough that it is able to encode sentences about arithmetic, meaning like it is able to talk about things like whether or not a given computer program halts. Okay, that's really what I mean. I mean, what else is there to arithmetic? Besides computer programs and whether they halt. Okay, I mean, powerful enough to to sort of express sentences like this Turing machine runs forever, or this Turing machine halts, something like that. Okay. So it's if a system can't even talk about statements like that, then it's clear that it's not. I hope we agree that it's then not talking about all of math, right? Because whether a Turing machine halts or doesn't halt seems like a perfectly reasonable mathematical question that you could ask, right? So we're saying if your system is sound, it's computable, and it captures, ordinary arithmetic, for example, questions about, whether computable processes halt or not, then it cannot be complete, okay? Then there must be, statements that, it can neither prove nor disprove, okay? So it sounds like there's a lot of conditions in this theorem. There's a lot of fine print here, right? Which, by the way, we know when people popularize Gödel's theorem, they often leave out the fine print. Okay, but let me, maybe to help build your intuition about it, let me let's convince ourselves that if we removed any piece of this fine print, then the theorem would actually be false. Okay, so first of all. Can we get a computable system that captures arithmetic and that's complete, but we just give up on soundness? It just doesn't have to be sound. Can anyone give me an example of that? I'll let you give up on consistency too. Yeah.
Just say that all propositions are true.
Excellent example. Just say everything is true. A is true, not A is true. But you just proved a contradiction. That's also true. There's a classic joke along those lines, right? Okay, so good. All right, so obviously we need to assume soundness. All right, what if we took away the assumption of computability? What then? Can anyone give me an example of a sound, complete proof system that captures all of arithmetic, but that just isn't computable? We just give up on there being a computable way to list all the theorems. Yeah?
To decide whether something is true or not, you just iterate through all of the possible rules of inference, and you try every possibility. And if you can finally get the sentence, you halt. Otherwise, you just conclude.
Yeah, okay. I mean, I think you're headed toward the right idea, right? Which is that we can take sort of a Platonic proof system, right? Like I will take a proof system whose axioms are just, and which are the same thing as its theorems, okay? Whose axioms are just all of the true statements of arithmetic, okay? There. I just defined it, right? I've taken, Fermat's last theorem, you tell me it's true, good, then that's an axiom, right? As soon as I know something is true, then it's an axiom of my system, okay? So I just take all the true sentences about arithmetic and none of the false ones as my axioms, all right? I can I can talk about that as as some mathematical entity, the set of all the true statements of arithmetic. By definition, it will be sound, and it will capture arithmetic, and it will be complete. The only problem, quote unquote, is, well, I've just defined the problem away, right? How do I actually figure out which sentences are true, right? How do ultimate, and this sort of shows us that ultimately, we want more from a proof system than just that it sort of platonically captures all the true statements. We need some actual way to derive true statements, by some computable process. Okay, and people sort of groped around by, what did they mean by a computable process for a long time. And then once Turing machines were invented in 1936, then people like Gödel said, aha, this is what we meant. Okay, that, there ought to be a Turing machine that lists the theorems. All right, how about a sound, computable, and complete proof system, but that just doesn't capture arithmetic? Let's just say that captures something weaker. Anyone know an example of that? Sound, computable, complete, but it's just going to be too weak to talk about arithmetic. Okay. Okay, so I'll give you an example of such a system. If we just consider, Boolean logic, or another, which is also called propositional logic, okay, where, we don't have any quantifiers, like for all, or there exists, right? The only thing that we have are sort of, we have some set of symbols, like x1 up to xn, okay, and then, we're allowed to, a true sentence is something like either x1 or not x1 is true, right? And, either x2 or not x2 is true. Okay, and you can write down, a set of rules of inference for this system, right? For taking true statements and deriving other true statements. For example, from these two statements, we could derive that either x1 or not x1 or x2 or not x2 is true, right? Or in fact that that even that this sentence is true. Okay, so this will be sound. Will only prove true things. It will. You can also write down a set of inference rules here that are complete. Okay, that will. Every sort of logical. So sort of every true Boolean statement you will be able to derive from these axioms, right? It's it may take an exponential number of steps, but you'll be able to do it, right? And it will be. And it will be computable, okay? And sort of the only problem, quote unquote, is that this is just a very weak language, right? This is not powerful enough to say things like, this given Turing machine halts, eventually, in some amount of time, right? There's just no facility in this language for making statements like that, okay? So, all right, so how did Gödel prove the first incompleteness theorem? Okay, so basically, for given any formal, given any proof system F, he showed how to construct a purely, arithmetical sentence. So just a purely mathematical statement, but whose meaning is, this statement is not provable in F. Okay, and so there were two sort of technical issues that you have to deal with in order to sort of express this statement, right? The first one is to get rid of the self-reference. Okay, but we already saw how to do that, last week. You can basically just say, the following statement repeated twice, the second time in quotes, is not provable in F. The following statement repeated twice, the second time in quotes, is not provable in F. Right, so you can, use that same trick that we saw before to sort of get rid of the self-reference. Okay, but then, there's still the bigger problem of, how do you express the concept of provability, right? And so what we saw with like Tarski's theorem last week, right? That there is no mathematical, definition, like within a formal system, there is no mathematical way that you can define the set of true sentences of arithmetic within the system. Okay, and the reason is that, if you could do that, then you could actually construct the paradox of the liar, and you would actually, this sentence is not true, and you would actually get a contradiction. Okay, but now what Gödel did, the key innovation here is to shift attention from truth to provability. Okay, and then what he did is he explicitly constructed, how you can construct a mathematical definition purely within the system F for what it means for a given statement to be provable in F. Okay, and so his original proof for that, it took like 30 pages of just like in retrospect, looks like like a CS person might look back on and say this was an incredibly inelegant hack. Okay, because basically what he had to do is he wanted to sort of reason about computer programs before the concept of a computer program existed. Okay, or this is sort of an anachronistic way of looking at it. Okay, but I think this is essentially what he was doing, right? Like he didn't have the concept of computer programs that just read in a sentence, which is like a string of bits, and do something with that sentence. And so what he had to do was just sort of say, well, look, every sentence can be, the set of all the sentences of the proof system F can be placed in one-to-one correspondence with the positive integers, right? And then, saying like that a given sentence S is provable in a formal system is just making some arithmetical claim about the integer corresponding to that sentence. Okay, and so basically to do this, he had to sort of construct a programming language that just operated directly on integers. Okay, and the way that this language worked is basically that you use like prime numbers to correspond to the different elements of your statement, and then to put them all together, you multiplied them together in some way to get a composite number. Okay, it's kind of like when I was just learning programming, like as a kid, and like I had a friend was also learning programming, and he was really extremely good at math. Okay, but he had never learned what an array was. Okay, so at one point, he needed an array, although he didn't know the name for it. So he just said, to each thing that could be in my array, I'll associate a different prime number, 2, 3, 5, 7, and so forth. And then I will, multiply them all together, and this will give me my array. And whenever I need to know what's in the array, I'll just factor it back into primes. Okay, this is, I don't, this is not considered good programming practice. If you had a quantum computer, it wouldn't be quite as bad because at least the factoring would be more efficient. Okay, but the point is, it's terrible programming practice, but it's sort of, it works. Right, so if you don't care about efficiency, or about memory management or whatever, it works. Okay, so this is essentially what Gödel did. He sort of constructed a programming language, just using like addition and multiplication of positive integers. Okay, but with the benefit of hindsight, we can be sort of much, and with the notion of a computer program in hand, we can be sort of much more elegant in how we talk about these things. Okay, so what we can do is say, well, look, we have assumed, as conditions, in this theorem that first of all, our proof system F is computable. And second of all, that it that is able to talk about things like whether Turing machines halt. Okay, so now under those two assumptions, what is the mathematical meaning of the statement S is consistent, where S is S is provable, where S is some sentence of the formal system S. What does it mean to say that S is provable? It means, it means that a certain Turing machine halts. Okay, which Turing machine? Well, there's a Turing machine that searches, that enumerates all of the theorems of F and that halts if it ever finds S. Okay? So, we've assumed that such a machine exists. Okay? And and we've also assumed that F is powerful enough to talk about such machines and whether they halt. Okay? So, which means that, under those assumptions, within F, we can make a statement like M halts, okay, which then amounts to saying that S is provable, right? It's just saying that if I enumerated, all, starting from the axioms of F, all of the possible consequences, all the possible results of applying the inference rules of F over and over, I would eventually hit S, okay? So this is the point, right? Provability, unlike truth, is not some metaphysical statement, right? It's just a statement that, you write a program that derives all the consequences of your axioms. That program will eventually halt and find the theorem that you want. Okay, so provability is itself a mathematical question. Okay, that's the key insight. Okay. Okay, and so now what do? Well, now we just, go through the logic, right? And we ask, okay, this sentence G of F, which is called the Gödel sentence, is it itself provable in F? All right, well, what happens if it's provable? Anyone? Yeah? Yeah, well, if it's provable, then it's not true, right? It says that it's not provable. So if it's provable, then G of F is false, okay? Which means that our system has proved a falsehood, right? It's proved something that's not true, which means that F is unsound, okay? Contradicting our starting assumption. We can't yet conclude that F is inconsistent, okay? We'll get back to that later, okay? All right, so what's the alternative? Well, the alternative is that G of F is not provable in F, right? When I say provable, I really mean just provable in F. Okay, that's important because, the same statement could be provable from one set of axioms but not provable from another set. Okay. Okay, but what can we say about G of F's truth if it's not provable in F? It's true. Yeah. Okay, which then, means that we have an example of a true but unprovable statement. Okay, and since F is sound, it can't prove not G of F, right? Because that would be false. Okay, so F proves neither G of F nor not G of F, which means that F is incomplete. Okay, so that's the first incompleteness theorem. So let me now show you a really, really pretty connection between Gödel's theorem and the unsolvability of the halting problem, okay? Showing how, actually once you know the unsolvability of the halting problem, then you can actually derive Gödel's theorem from that, or the first incompleteness theorem, but in a different way than the way that we just did. Okay, so how could we, how do you prove that A implies B, where A and B are both impossibility statements? Anyone want to just answer that general question? What's the first thing we try? Well, we can, right? But even more basic than that, we take the contrapositive, right? We try to show that not B implies not A, okay? So what we want to do is to show that, suppose that we had a sound, computable, complete proof system that captured arithmetic. I'll just call that an awesome proof system, okay? I would like to conclude from that then we would have a Turing machine to solve the halting problem. Okay? That's my claim. So given such a powerful proof system, how could we use it to solve the halting problem? Anyone see that? Okay, you've got a system which is able to reason, express statements about Turing machines, right? It's everything that it says is true, and given any question that you can put to it, it gives it, it either proves that the answer to that question is yes or no. All right, are we getting warmer here? Yeah.
Ask it if any machine runs.
Okay, right. So we're given a Turing machine. We're given as input a description of a Turing machine M, right? The halting problem is to decide, let's say, whether M halts on a blank input, right? Okay, but now we've assumed that there is a Turing machine. All right, let me call it P, I guess, that lists all of the theorems of F. Okay, and because F is complete, at least one of those theorems must be either M halts or M runs forever, right? Otherwise, it wouldn't be complete, right? It would, it would fail to decide the question of whether M halts. Okay, so this means like logical, this symbol means sort of something is provable from the axioms of P, right? So it must either be the case that P proves that M halts, or that P proves that M loops. Okay, and furthermore, because F is sound, whichever one is, as soon as we found a proof of either of these, we would know that that thing was true. Okay, right? Whatever F says is true. Okay, so now our algorithm for the halting problem will simply be just enumerate all of the possible theorems of P, which because F is, enumerate all of the theorems of F, right? Which because F is computable, we know that there's a program P that does that. Okay, and then eventually we must halt, finding either a proof that M halts or else a proof that M runs forever, and then we know the answer. Okay, so but we already know that the halting problem is uncomputable. Okay, and from that we conclude that this awesome proof system cannot have existed. You see that? Okay, this algorithm is sometimes called the British Museum algorithm because it's just the British Museum is supposed to have like a a sample of everything. I've been there. It doesn't really, but it does have a lot of things. Okay, and so you just look through every possible proof and disproof in your formal system. Okay, all right, good. So. So let me actually ask a more refined question, which someone asked me after class last time, and it's an excellent question. Okay, you know, and this is also one that Turing answered for the first time in his 1936 paper. Okay, you might say this. Okay, you might say, look, we know from Gödel's theorem that there can't be any, you know, sort of. I mean, we know from Gödel's theorem that given any reasonable, you know, proof system, you know, to capture arithmetic, right, there are going to be statements that proof system doesn't decide one way or the other, right? They'll be, you know, they'll be undecidable. Okay, but you know, the examples that Gödel's theorem produces are pretty damn artificial, right? You know, I mean, it's not, you know, normally when you're doing math, like you're not going to run into a sentence like that one by accident, okay? That, you know, asserts its own unprovability, right? It's the kind of thing that, you know, you're only going to find if you were looking for it, okay? So maybe, you know, we can just sort of cut these out, you know, like a cancer, right? Just cut them out of math and just get rid of them, right? Okay, and you know, so a very nice goal that you might have is, you know, couldn't we build a machine? So let's say a Turing machine, since you know that's our modern definition of what a machine means. Okay, couldn't we build a Turing machine M that takes, you know, written on its tape an encoding of a mathematical statement S, and that then sorts S into one of three categories. Okay, it tells you whether S is provable in your favorite formal system, like, you know, piano arithmetic or whatever, or it tells you that S is disprovable in that formal system. Okay, or, you know, we know that there's a third possibility. It could tell you that S is a weird Gödel sentence, okay, and is neither provable nor disprovable. Okay, but whichever of the three it is, this Turing machine will tell you. All right. Well, unfortunately, and this probably is not going to shock you at this point, I claim that this Turing machine cannot exist either. Okay, you can't even have this three-way sorting machine. Okay, now why can't you? Does anyone see why not? All right, let me give you a hint. Does anyone see how if we did have such a, you know, even this Turing machine, then we could use it to solve the halting problem? So, yeah.
Well, it seems like this almost just is the halting problem. Like,
Yeah.
if it's provable or disprovable, then there's a Turing machine that halts, and if it's a weird Gödel sentence, then there obviously is a Turing machine that doesn't halt.
Yeah. Okay. So we're given as in. Okay. Yeah. So I think you got the essential point there. So we're given as input a description of. All right. So I keep flipping between M and P, but whatever. Machine and program, they're interchangeable. Okay. So we're given as input a description of a Turing machine P, right? And the question that that we want to know the answer to is whether P halts on a blank input or not. Okay, and we need to use this machine to answer that question. Okay, so what do? Well, we just ask the machine, you know, so what about the sentence that says that P halts? Is that provable, disprovable, or weird Gödel? Okay, and then, you know, we will just go through the three possibilities. If it's provable that P halts, well, you know, we've assumed that our system is sound, right? So then, okay, P halts. That's fine, you know, and then we can, in that case, we can even confirm it for ourselves if we want by just simulating P until it does halt, right? If it says that P, you know, that it's disprovable that P halts, well then, you know, since it's sound, then, you know, P must run forever. Okay, but what if it says that whether P halts is a weird Gödel sentence? Okay, what can we then conclude about the truth of whether P halts? This is sort of the key point here. Okay, well, you know, if it says that it is unprovable whether P halts or doesn't halt, then from that very fact of the unprovability, we can conclude that P cannot halt. Okay, why? Yeah.
Because if it halted, we could just observe it halting.
Exactly right. Because if it halted, then surely there would be a proof that it halts. The proof would simply consist of simulating P for a finite number of steps and just, doing a trace, of it for step by step by step until you see that it halts. That's a finite, So any time, in other words, you have any, reasonably powerful proof system, that really doesn't have to be very powerful, right? Anyone worth its salt, then any time a Turing machine halts, that system can prove that it halts, because you just say, well, look at the thing, here's the execution trace. Go watch it, and you see that it halts after this number of steps. Okay, which means that if a sentence of the form P halts is formally undecidable, then the truth must be that P runs forever. Okay, which is a cool fact, right? And and it's not often sort of missed in discussions of logic. Like there was a whole novel called Uncle Petro's and Goldbach's conjecture about a mathematician who's obsessed with proving Goldbach's conjecture, and at some point he thinks, okay, well maybe it's just unprovable, right? It's just independent of the axioms of set theory, right? Which is that's a logical possibility for any famous unsolved math problem of your choice, right? Yeah, maybe it could be like the Gödel sentence. It could be just independent of set theory. Okay, but if your question is like Goldbach's conjecture, that is, if it can be phrased in terms of whether some computer program halts, then something very cool, which is that if you could ever prove that it was independent of set theory, then by that very fact you would have proved that the statement is true. Okay, you would have proved, that the program does not halt. In this case, that that yes, every even number is expressible as a sum of two primes. All right. So now there were two kind of improvements that I want to make to Gödel's theorem. Okay, I mean, I'm not the one who made them, but but two improvements that we should make. Okay, the first one is that we had to assume that our system was sound. Okay, and that's kind of unsatisfying because, as we discussed last week, soundness is is this meta mathematical notion, right? We can't even define within F what it means for F to be sound. Right, only sort of looking outside of F can we even define that. Okay, what would be much more satisfying would be if we could merely assume that F was consistent. Okay, because consistency, unlike soundness, can be defined purely within F. How do you define like what is the meaning of saying that F is consistent? Let's say in terms of Turing machines. It means that when you take the computer program that just lists all the theorems of F, then that computer program never derives a contradiction, right? Or never derives both a statement and its negation. Okay, so again, that's just a mathematical claim about the behavior of the computer program. That's not any sort of philosophical claim. Okay, so let me actually. I can just cross things off to do what I want. Okay, so there's an improvement to Gödel's theorem called Rosser's theorem from 1936, and it just says that we can weaken soundness to consistency. Okay, so Gödel was part of the way there, but the full it took Rosser to sort of complete the argument. Okay, so no consistent and computable proof system that captures arithmetic can be complete. All right, so how do we prove this? Well, it turns out that we need a tweak to this Gödel sentence, G of F. Okay, we have to go back to it. And the problem with the Gödel sentence is sort of that there's a big asymmetry in it between provability and unprovability, right? It says that it's not provable, but it doesn't say anything about, that this sentence is not disprovable, right? And that asymmetry in some senses is the source of the problems. Okay, so, you could try to say this sentence is neither provable nor disprovable in F. But you can try it. That doesn't really work either. Okay, and then Rosser sort of figured out the right way to do it, which is, it's not what I would have guessed immediately. See if you would have guessed it. You say, for every proof of this sentence in F, there is a shorter disproof of this sentence in F. Okay? And that's what we'll call the Rosser sentence of F, R of F. Okay? And, it shouldn't surprise you that once again, you can, eliminate the self-reference in the sentence using the recursion theorem trick. And once again, you can express the concept of, having a proof, having a shorter disproof, and so forth in purely mathematical terms, using these coding tricks, using the fact that F is powerful enough to talk about computer programs, and computer programs are powerful enough to enumerate all of the theorems of F. Okay? So now all that remains is to walk through the logic of this Rosser sentence, okay? I know it's early in the morning, but, are you ready for this? Because this is a, this is a good one. All right. So let's first, I claim that, assuming, only that F is consistent, then this R of F can be neither provable nor disprovable in F. Okay, so it must be independent of F. Okay, and we're only going to use that F is consistent here. Okay, so it'll be a proof by contradiction. We just have to consider both cases. First, let's suppose that R of F is provable in F. Okay, then what can we conclude from that? Anyone? Well, yeah, it's okay. If R of F is provable, then it's provable, and we've now proved a theorem that says there is a shorter disproof of me. All right. So now what can you do? Right. Well, now here's the key point. Right. However long So let's say that R of F is provable by a proof which is k bits long. Okay? Then here's the key point. There are only finitely many possible strings that could be the shorter disproof that's being talked about here. Right? We only have to consider strings of k-1 bits or fewer. Okay? And there's only finitely many of them. Okay? So now what you could do is just enumerate all of those possible strings, of length less than k, and just check whether any of them is a disproof of R of F. Okay? Well, suppose that one of them is. Then what can we conclude? That yes, the F is then inconsistent. Okay? But suppose that none of them is. Then what can we conclude? Yeah, then it also, in fact, in that case, it also follows that F is inconsistent, okay? Why? Because, not only did F sort of say something that was false, but it's something that sort of contradicted a finite number of statements that, we were able to check for ourselves, okay? So, the only time you got to worry about the difference between consistency and soundness is when you could have a formal system that says something like this program halts, right? And then in fact it never halts, but no matter how long you run it, you still haven't proved that it never, you still haven't proved that it runs forever, so you're never going to catch it in the lie. Okay? So that you worry about. Okay, but here, R of F said something. It said that there's a shorter disproof, but there were only finitely many cases to check, and we checked them, and none of them was that disproof. Okay, and that amounts to a contradiction. Okay, that's that's now we can now just write out a finite proof that that R of F because presumably F also proves that none of those shorter sentences were disproofs, right? Because those are that's just a very that's just those are just immediately checkable statements. Okay, so but because R of F also proves those other statements, that means that it contradicts itself. Okay, and it says that there's a shorter disproof, but then for every particular shorter string, it affirms that it was not a disproof. Okay, so conclusion: F is inconsistent. All right, let's consider the other case. Suppose that R of F is disprovable. Okay, then what can we conclude? Then then F has proved a theorem that says what? Well, it said that F has then proved that there is a proof of R of F that has no shorter disproof, right? That's the opposite. Not R of F is there exists a proof of this sentence, namely of R of F, that has no shorter disproof. Okay, so now we have a theorem saying that there is a proof that that has no shorter disproof. Okay, so now let's think about this. So let's say that but we just found a disproof. We just assume that there is a disproof of F, right? So let's assume that disproof is k bits long. Okay, and so now so there's a k bit disproof. Okay, but there's also a proof that has no shorter that has no disproof which is shorter than it. Okay, so now we can ask, well, how long is that proof? Right? It says that there is such a proof. Okay? Well, there's two possibilities. The proof could be longer than k bits, but in that case, we've just derived a contradiction, right? Because we have this long proof, because the shortest proof, let's say, of R of F does have a shorter disproof. Okay? So and that's a contradiction that F itself can see. So the other possibility is that shortest proof of R of F is shorter than k bits long. Okay? That's the only remaining possibility. Okay, but in this case, we can do the same thing that we did in this other case. We can just enumerate every possible string of k minus 1 bits or fewer, and just check whether any of them is a proof of R of F. Okay? If any one of them is, then we have derived a contradiction, because then we have both a proof of R of F and a disproof. Okay, so F is inconsistent. But if none of these is a proof of R of F, then then F is just lied to us, and we've caught it in the lie. Okay, it said that there was a proof that had no shorter disproof, and we checked. If there was such a proof, it had to be one of these strings, and we checked all of them, and none of them was. So F has contradicted itself. Okay, so it's inconsistent. Okay, so we conclude that no consistent, complete proof system can capture, no complete, consistent, computable proof system can capture all of arithmetic. Okay. All right, but now there's one other improvement that I want to make to Gödel's theorem. I wrote before the first incompleteness theorem. But as the name suggests, there's also a second one. Okay, the second incompleteness theorem, the starting point of it is, something that, if you thought about these arguments that, we were making here, might have seemed a little bit funny to you, okay? And that's that, well, we went through this whole argument to say that, why G of F is, cannot be provable in F. Assuming that F is sound or whatever, or why R of F cannot be provable in F, assuming that F is consistent. Okay, but wait a minute. In making this whole argument, didn't we actually prove G of F? Right? Because we showed that that F can have we showed that G of F can have no proof, but that's exactly what it says. So didn't we just prove it? But wait, but if we did prove it, then then we just got right back in the contradiction, right? So what gives? What's going on there? Okay. Well, in fact, there's a little subtlety. In fact, this argument did not quite prove G of F. Okay. Why didn't it prove G of F? Well, because in order to derive from this whole argument that G of F was true, I sort of covertly slipped in the assumption that F is sound. Okay, if F is not sound, then then it could very well be that that F is just wrong about something, right? So like it could, if F were unsound, then it perfectly well could prove G of F. Okay, and in fact, if F was inconsistent, an inconsistent system proves absolutely anything, right? So once you all know this, right? Once you have an inconsistency, you can derive anything, right? Like Bertrand Russell's famous, example was, okay, I can derive anything from 1 + 1 = 1. And then someone said, okay, great, prove you're the Pope. So he said, I am 1, the Pope is 1, I and the Pope are 1. Okay, so if F was inconsistent, then surely F could prove R of F. Could also prove not R of F. Okay, so it is only so the conclusion that we can derive is only a weaker one, okay, which is that F, in F it is possible to prove. So let me introduce a notation. Con of F means that means the statement that says that F is consistent. Okay, which again is a mathematical statement that you can formalize purely within F. Right, it just says that a Turing machine that looks for a contradiction, within all the theorems of F is never going to halt and find one. Okay, so F proves that if F is consistent, then the Rosser sentence of F holds. Okay, so if because right, so we can go through the argument, right? If F is consistent, then there can be neither a proof of R of F, nor a disproof of R of F, right? We just saw that before, okay? But if there's neither a proof nor a disproof, then in particular that means R of F is true, right? Because it says for every proof of the sentence there's a shorter disproof, but if there's no proof and there's no disproof, then that's sort of just trivially satisfied, okay? So. And furthermore, that entire argument that I just made just now can be formalized within F itself, okay? Assuming that F is powerful enough to be talking about these things in the first place, okay? So which means that F proves that that the consistency of F implies the Rosser sentence of F, okay? And in fact, F even proves that these two things are equivalent to each other. Okay, I can leave it as an exercise for you to show how, assuming, let's just do it right now. Why is it true that assuming the Rosser sentence of F, F must be consistent? Anyone? Well, once again, let's take the contrapositive. Suppose that F were inconsistent. Then why would the Rosser sentence be false? Or oh, I'm sorry. That doesn't. This should have been g of f. I'm sorry. That actually doesn't work. Okay, that's okay. So all right, and then I would need a modification of it. All right, you know what? Forget it. Let's just do the arrow in one direction. Okay, so f proves that if f is consistent, then the Rosser sentence holds. Okay, but now what does this mean about can f prove con of f? Okay, suppose we had a proof of f in con of f, then what would we also have? Okay, from this we see that if f were able to prove its own consistency, then f could also prove the Rosser sentence. But then that would mean that f was inconsistent. Okay, so the second incompleteness theorem is a statement that if f is consistent, and it satisfies those other conditions, that it's computable and that it captures arithmetic, then f cannot prove its own consistency. Okay, so it's not just that there are these unprovable sentences. At least one of the unprovable sentences is actually quite interesting. It's the one that says that the system itself is consistent. Okay, and this is a form of Gödel's theorem that you may have seen before. It says that no powerful enough formal system is able to prove its own consistency. Okay, so now this is by the way, like even if f had proved its own consistency, like it's not clear why you would want to believe it, right? Because if you didn't already believe f is consistent, well then okay, right? Anyone can say they're consistent, right? But it would be a nice kind of self-referentiality, a nice kind of closure if you had a system that was able to prove its own consistency, and that is part of what Hilbert hoped for in the year 1900. And the second incompleteness theorem says that you cannot have that. Okay. By the way, ironically, you can have a system that proves its own inconsistency. Okay, that's totally fine. Okay, so what's an example of a system that proves its own inconsistency, but is okay? Or I should say is consistent, is nevertheless consistent. Okay, you can take. Let's just take any formal system f to which Gödel's theorem applies, like piano arithmetic or whatever. And now let's just take what I like to call the self-hating theory. Okay, this is f plus an axiom that says f is inconsistent. Okay, so you just add as an axiom that there is a proof somewhere of f's inconsistency. Okay, so this is this is sort of this is a depressed proof system. It believes that somewhere out there is a proof of its own inconsistency, even though it's never found one. Okay, it takes that as an axiom. All right, so I claim that assuming that f is consistent, that this enlarged system is also consistent. Why is that? Anyone? Can anyone see why this? Yes.
Because it can't prove that it's consistent, so if there's nothing to contradict the axiom that it's not consistent.
Exactly. Because if you could derive an inconsistency in this system, then from that, that would amount to a proof of conf, right? We would have assumed not conf, and we would have gotten a contradiction, so that would have meant that conf is true. But then f would have proved its own consistency. And the second incompleteness theorem says that it can't do that if it's consistent. Okay? So, which means that the system f plus not conf, has to be consistent. Okay, so this is, I feel like there's a moral lesson in here. Okay, like the ones who boast of their own consistency, are the ones who have nothing to boast of. Okay, and in fact, the only belief about your own consistency that can keep you consistent is that you're not consistent. Okay, so good. Okay, so just a few words about how this plays out in practice. So I mentioned before that probably the two most popular proof systems that there actually are that sort of are have been the foundation of math for more than a century are piano arithmetic, which is a system for reasoning about positive integers, basically using first order logic, and then ZF set theory, which is a more powerful system which is able to reason about sets. Okay, including infinite sets, different sizes of infinite sets, and so forth, which are much larger objects than piano arithmetic knows how to talk about. Okay, now the second incompleteness theorem says that no consistent proof system can prove its own consistency. If it's above a threshold of power, which all of these systems are above. Okay, so for example, piano arithmetic cannot prove its own consistency. Okay, on the other hand, there are axioms that we could add to piano arithmetic, such that we could prove that PA is consistent. What's a more powerful? What's a way that we could strengthen PA so that con PA would be a theorem? Anyone have a really, really stupid way to do it? Really naive way to do it? How about if we just tack on con PA as an axiom? Okay, you can always do that. You could always just take the system piano arithmetic plus, I'm just going to assume as an axiom that piano arithmetic is consistent. Okay, now, unlike what we did here, this doesn't create a contradiction because it's not that piano arithmetic has proved its own consistency. It's just that we've tacked on the consistency as an additional axiom. Okay, that doesn't lead to any contradiction, necessarily, and and this system, of course, by definition, is able to prove that PA is consistent. Okay, that's one of its axioms. Why have we not now contradicted the second incompleteness theorem? Why is this system not now just proven its own consistency in violation of Gödel? Yeah. Well, no, actually, this system, as far as anyone knows, is perfectly consistent. Consistent, even sound. In fact, if you believe piano arithmetic, presumably you also believe piano arithmetic is consistent, and therefore you also believe in the truth, the soundness of this enlarged system, right? It's just, you believe piano arithmetic is sound and consistent and all that, then, you have to believe in this, right? So, but, why does this system not prove its own consistency in violation of Gödel's theorem? Yeah. Well, it's certainly incomplete, right? But the second incompleteness theorem said something more specific. It said that none of these systems can prove their own consistency. I'm asking, why does this not prove its own consistency? Yeah.
By tacking on that axiom,
yeah.
It's no longer just piano arithmetic.
Exactly. That's exactly it. This system proves the consistency of piano arithmetic, but that is not the same as proving the consistency of itself. Okay, because itself is no longer piano arithmetic. Itself is now an enlarged system, PA plus con PA. Okay, and that is a more powerful system. Okay, so if you wanted to, so this system is able to prove the consistency of something weaker than itself. namely PA. And that's totally fine. There's no contradiction with Gödel there, right? A system can prove the consistency of a weaker system. That often happens. Okay, it's just that it can't prove its own consistency. So if we wanted to know that this system was consistent, then what new axiom would we have to add? Well, we could always just add on another axiom saying, well, this system was consistent too. Okay, we could say PA plus the axiom of PA's consistency gives rise to a consistent system. All right, well, now this system can prove the consistency of PA plus con PA. Okay, it still can't prove its own consistency, right? You would then have to add on the axiom con of PA plus con PA plus con PA plus con PA. Okay, and so forth. So, so the picture that Gödel's theorem gives you is an infinite hierarchy of more and more powerful formal systems, okay, where each system in the hierarchy is able to prove the consistency of all of the systems lower in the hierarchy than itself, okay, of all the weaker systems. But it cannot prove its own consistency, or of course the consistency of any of the higher systems in the hierarchy. Okay, so these are called iterated consistency statements, right? So this is the picture that Gödel's theorem gives you, right? It's not that that there are statements that have to be forever unprovable, like no matter what axioms you add. In fact, given any statement of your choice, there's some axiom that you could add that would decide that statement. If nothing else, the statement itself, or its negation, okay? But it's saying that no one proof system is going to be able to capture all of mathematical truth, right? You're always going to, there's always going to be something additional that you have to add on. And then even after you've added it, then there's something additional that you would have to add on, again, yeah.
Is there any possibility of just formulating your system to be slightly differently so that it's easy to prove different things?
What do you mean?
So like, so suppose you have like a current system F, and it can prove a certain set, and like there's certain statements that it can't prove. You don't know what they are, but
right. Yep.
And then you make another one like G or something, or E or whatever.
Yep.
And that one can prove those statements, but it can't prove other statements that are provable.
Yes. You can have like multiple. Incomparable systems, right? You can have like two systems where each one can prove statements that the other one can't prove. Okay. On the other hand, if you have like one system that that proves like the consistency of a different system, right? Then then in some sense, like if A proves that B is consistent, right? Then there's some sense in which A is like at least as powerful as B. Like A, sort of knows everything B knows. It's not literally that A can prove everything that B can prove, but sort of A can mimic everything that B can do. Okay, so yeah, okay, so now another thing that's true is that if you're in set theory, then in fact you can quite easily prove the consistency of piano arithmetic. Okay, a way you can do that, so like in order to show that a set of axioms is consistent, right, it always suffices to just give any example of an object that satisfies all of those axioms, right? We call that a model of the axioms. Right, in fact, that's what it means for, Gödel proved another thing called the completeness theorem, which was, the incompleteness theorem was his PhD thesis. The completeness theorem was his master's thesis. Okay, it was, it was the warm up. Okay, then the completeness theorem basically says that a set of axioms is, in first order logic is consistent, meaning, it cannot prove a contradiction if and only if that set of axioms has a model, meaning, like there is actually an object that satisfies all those axioms. Okay, and so to prove something is consistent, it suffices to give a model, and now a model of piano arithmetic is the set of all the positive integers, right? Not surprising, right? That's what they're supposed to be talking about. So, not surprising that they would satisfy the axioms. Okay, and in ZF, because ZF is able to construct infinite sets, it's able to just construct the set of, explicitly, the set of all the positive integers, and then you just check that that set satisfies all of the axioms of piano arithmetic, and then it follows that piano arithmetic has a model, and therefore it's consistent. Okay? You can't carry out that proof in piano arithmetic because piano arithmetic is not able to talk about infinite objects, like the set of all integers. It's only able to talk about, this or that integer, integer x, integer y, and so forth. Okay, so PA cannot prove its own consistency, but ZF can prove PA's consistency. Okay? Can ZF prove ZF's consistency? Well, we know the answer from Gödel's second incompleteness theorem. No, it cannot. Okay, there are more powerful set theories that can prove the consistency of ZF set theory. Okay, basically what you can do is you can postulate what's called a large cardinal. Okay, when set theorists say large, they really mean large. Okay, what does large mean here? It means larger than any infinity, than all the infinities that could be defined in ZF set theory. Okay. That's their definition of large. Okay? What? No, it's not. No, it's not. You can, it's not, it's not this an infinity larger than all infinities. It's just an infinity larger than all infinities that are definable in ZF. Okay? So, of course, this infinity is not itself definable in ZF. Okay, but fine, we can have a more powerful system where we, ZF plus large cardinal axiom, where we postulate that there is an infinity larger than anything definable in ZF, right? And then in that new, more powerful system, ZF plus the large cardinal axiom, we can actually prove the consistency of ZF. Because using that gigantic, bigger than ZF infinity, we can construct a model for ZF, that has all of the infinities that ever occur in ZF, and then that proves ZF is consistent. Of course, this system can't prove its own consistency. If you want this, if you want to know that this is consistent, you need to postulate an even larger cardinal, okay? Extra large cardinal, okay, and so forth. All right. So in the remaining 5 or 10 minutes, I want to do sort of our last topic on logic, and this will be a sort of a very, very nice transition into complexity theory, which will be our next unit. Okay, and this is Kolmogorov complexity. Okay, and this is a sort of a beautiful notion that was invented in the 1960s, and that really sort of helps is another way of making quantitative these notions of computability. Okay, by the way, we already saw another way of making these concepts quantitative, which was the busy beaver numbers, right? So on your third PSAT, you're going to have a really fun problem, I think, which is to show that once the busy beaver numbers get large enough, once they exceed some finite value, then the values of busy beaver of n, whatever the value is, it's no longer provable in any standard system of set theory. Okay, that's how big they are. Okay, now we don't know a concrete bound on the value of it, the least value of n for which busy beaver of n is independent of set theory. Okay, certainly it's more than 4 because we know the first 4 values, right? But it's probably a lot less than 1 million or something. Okay, Adam, your TA, is working on a project right now to get the first concrete bound on that n. So. Which I think is a fun thing to do. Okay, I'm not sure if he agrees, but okay. But now we're going to talk about another way of making sort of computability theory quantitative, and this is Kolmogorov complexity. Okay, and what we do here is basically, if I'm given a string x, let's say a string of n bits, okay? The Kolmogorov complexity of x is basically just the length of the shortest computer program whose output is x. So in other words, it's the number of bits in the shortest computer program, p, such that when you run p on an empty input, then p halts and outputs the string x. Okay. Now, there is a question here. Okay, length of the shortest program. That's great. Which programming language are we talking about? Right, the length of the shortest C program might be different than the length of the shortest, Haskell program, right? If I wrote if I defined a programming language that just had like a command, print War and Peace, and you just, call that and it just prints the complete text of War and Peace, right? Then in that programming language, War and Peace has a really low Kolmogorov complexity. Right, but it would have a much higher complexity in a language that did not include that command. Okay, so what makes this notion of Kolmogorov complexity sort of sensible is a key result called the invariance theorem, which you're going to prove on p set 3. Okay, and basically what the invariance theorem says is that for any two programming languages, A and B, there exists some constant, C of A, B, depending only on the programming languages, such that for every string x, the length of the shortest program in A that outputs x differs from the length of the shortest program in B that outputs x by at most C of AB. Okay, so which means that sort of, yes, the choice of programming language can, change Kolmogorov complexity by an additive constant factor, right? An additive constant depending on your choice of programming language. Okay, but it's not going to change it by more than that. Okay, and so you'll see the reason in your on the P set. Okay, so let's.
But they didn't come with the mic, and I emailed them
see a couple examples. So what?
Microphone for it. He's like, no.
Let's say that I had a string of just n zeros. What does anyone think is its Kolmogorov complexity?
G2s now, they sell the G3s.
Roughly. I don't care about additive constants. Just how does it grow as a function of n? Like what is a short computer program that you could think of writing that would just print n zeros? Or how long would that program have to be? Yeah, it would have to be about log n bits long, right? Because it would basically just have to say, for I equals 1 to n, print 0, right? And the length of that program asymptotically, and the limit as n gets large, is just going to be dominated by the number of bits needed to specify n itself, right? The for I equals, print 0, that's just constant, that's just a constant amount of overhead. So we can say,
cool. But that first time, I don't know that time we put the shore on it.
That this string has low Kolmogorov complexity, or in other words, we could say this string is highly compressible. Okay, it's an n-bit string, but it can be fully described by giving a computer program to output it, which is only about log n bits long, right? Namely, a program that just says print n zeros. Okay, so we could say, on this basis, the string of all zeros is a highly compressible string. Okay. And this is meant to be suggestive because, in some sense, what Kolmogorov complexity is, what it's trying to capture is what is the ultimate theoretical limit of data compression. Okay, it's saying,
have us as ammo
you know,
in
if
that
you're
case.
allowed to use any kind of computer program you want, you know, to compress X, how, you know, how well can you compress it? Okay, you know, with the one caveat that the decompression program has to be included as part of your itself has to be included as part of the file size. Okay, now what if X is a random string? So what if I just pick a completely random string of n bits? What will its Kolmogorov complexity be, roughly,
So when
most
you
of the time?
go down Cardinal Medeiros where the Kendall Theater is,
Yeah.
you know, you hit Cambridge.
About n. So I claim
Right.
That's us in front of you.
I see.
Like, you probably passed
Unless you're like
that
right
for
next to
most,
place.
you know, n-bit strings X,
their house.
Right.
their Kolmogorov complexity
Take a right.
is pretty close to n. Okay, this is, you know, this requires a formal proof, but it's, you know, basically just saying, you know, a random file cannot be compressed. Okay, you know, this is a, you know, principle of data compression that some of you might know, right? There was a company back when I was in grad school. There was like got in the news and on Slashdot and stuff for claiming that they could compress a random file. You know, they had like an amazing compression program that could compress absolutely anything. And you know, and I read an interview with the founder of the company that, you know, where they were asking all these, you know, questions
You
like,
chose a
well,
good time
you
to
know,
leave.
but what do you say that these experts didn't validate your technology and blah 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 blah. And then finally, and you know, like after a long interview, the interviewer finally said,
several
listen,
ideas. I thought we could
if you could
discuss them at the
compress a
meeting.
random file, then why don't you just take the result of the compression and feed it back into your program?
Yeah.
And just, you know,
No,
feed it back
also
and back
total
and back until you would
replacements, yeah.
compress any file to nothing.
I don't
Right,
see
and the
how to
guy's like,
salvage that
say,
problem.
you know, hey, that's a trick question, you know. So
should've
all
done
right,
it a little
so
earlier.
that, you know, but that is a proof that, you know, there must be n-bit
Yeah.
strings whose Kolmogorov complexity is at least n, right? You know, so, you know, there cannot be a perfect form of compression. It would be great if we could at least know which
discovered
strings
a
are
bug in
compressible.
this lecture
You know the
about
Kolmogorov complexity
40
of any
minutes
given
ago.
string.
It's exciting.
Unfortunately, on Thursday, we will see that too is an uncomputable problem. And the proof will involve yet another logical
I'm
paradox.
also trying to get
Okay.
this level-linked B trees,
And then we'll start on complexity
which
theory.
I
All right.
covered last time, but didn't notice this bug. Turns out it only gets the finger search bound if you